In kinematics, we often graph data of the motion of an object, and it's important to be able to simply identify trends from that data that tell you indications about the object's motion, as well as make predictions about what will occur in the future. In doing so, it's important to note the three basic graph representations of motion. One is where we graph displacement as the dependent variable versus time, one where we graph velocity as the dependent variable versus time, and one where we graph acceleration as the dependent variable versus time. As such, these are referred to as a D versus T graph, a V versus T graph, and an A versus T graph. Each one of these graphs, it's important to make note of what the slope of each graph represents. In this case, the slope is displacement divided by time, which of course is velocity. Over here, the slope is the velocity change divided by time, which of course is acceleration. And I'll let you determine what that one is and if it's useful. Nonetheless, it is relevant in Physics 1 to be able to translate information presented on one graph into another, and this can most easily be done by analyzing the slope. On a D versus T graph, when there is no slope, there is no speed. Therefore, if the displacement remains continuous forever, the velocity remains zero forever. And so a translation of this trend line, no motion, translates onto the x-axis for the velocity versus time graph. Of course, an object that is not moving is also not changing its motion, and so therefore the acceleration would also plot onto the x-axis for this comparison. Similarly, a object can absolutely move. It can start at some displacement that is lower and then trend away, indicating that it is traveling. In this particular case, the displacement trend line is straight and specifically positive in its slope nature. If we were to calculate it, it is a continuous value all the way up, indicating that the velocity is in fact constant. The slope is constant, indicating over here on the V versus T graph, a constant value that would be represented as a horizontal line. In this case, the velocity as a constant value indicates the velocity is not changing. And so again, the acceleration plots on the x-axis with a value of 0. Now, when we do accelerate, it's clear that we would be changing speed. And so if we're changing speed or velocity, then our acceleration is going to exist. With a positive acceleration, we can imagine that we must be speeding up in terms of the velocity. So we would indicate that we would start with some lower velocity and accelerate up to some faster speed, ever increasing at a constant rate. Thankfully for us, in Physics 1, acceleration will either be a constant value, positive, a constant value, negative, or 0. And so we will never have anything other than horizontal lines on this graph. On the velocity graph, we can have 0 velocity, we can have constant velocity, we can have increasing velocity, we can have decreasing velocity. But in all cases, we would not have curves indicating a disproportionate rate change of velocity, which would indicate that the acceleration is changing. Again, Physics 1, acceleration is constant. Nonetheless, the trend of velocity ever increasing means that over time you are covering more and more displacement. This is covered in a formula that includes time being squared. This square term causes an exponential increase, which means that this trend line would graph more like this as an ever increasing sharper curve curving up. So we have exponential parabolic curves on the displacement graph. We have linear increasing velocity graphs over here and a constant acceleration over here.